Okay, so let's get started. All right. So you have already looked at complex numbers, and now we are going to complex variable, which is in chapter 14 of the mathematical methods for sciences, the book that I gave you by Mary Boas. So now this is in chapter 14. Complex variable is a very difficult topic. It is very normally you can study complex variable for a whole semester. So, but in this course, it is more of a design to give you an introduction to what is complex variables. And unfortunately, you won't be taking complex variable in your third year. It is only offered to the SSCZ groups. So you will see what it is. So basically, what I'm going to cover, what I intend to cover is just a very basic, the basics of complex variable. But if you have the time, you could actually look at the book, and you will see how it is related to the integrals that you have seen in the first our first topics, which is on vector analysis. Remember, you talk about the Green's theorem, you talk about the Stokes theorem, and so on. So there is a relation between a complex variable approach to solve the same problem, right? So we're not going to it because I think the other classes they are not that they do not put so much emphasis on this. So we will just stop at what is needed, and that's it for this topic. Right, so let's get going. Here, there is two parts which I have written here in the board. So the first part is we want to find the real and imaginary parts of a function, and then the other one is to introduce to you what is analytical function. Right. So let's go to the first one. That is the real and imaginary parts. So here you already know actually what it is. So let's take, for example, we have a function that depends on z squared. Okay, so this is a function that depends on the complex number, and so this is a complex function, right? So now z squared, if we expand this z as in a rectangular form, that is x plus iy. I remember you have a square here, so you have the square, and now you just have to expand this guy, and you have x squared plus 2xy I plus I squared y squared. And here you know I squared is equals to -1. So -1, this is going to be a real part of the complex number. So let's say this is a complex number, it's a complex function, but you can also call this as a complex number. So here now, this x squared minus y squared is going to be a real part of this complex function, and 2xyi, this is the imaginary part. So the whole point of a complex number is to now say that x squared minus y squared is another function which we call as a u, and u is dependent on x and y. Okay, so x and y is the real part of it's a real number in the complex number. So there's few things to differentiate here. Okay, so x and y is a real number. Okay, this is not the same as a real part. So real part of a complex number, the real part of a complex number is x, but x and y is real number. So this u is a function of real number x and y. And then 2xy, which is the imaginary part of this complex number here. This we will write it as a function v. So now this is vxy, right? So now the starting point of a complex variable is to write a function in terms of a u and v, right? Let's say we take, for example, now z. So we have a function of complex number z alone. So now this is going to be x plus I y. So now this is going to be your u, and this is going to be your y. V. Sorry, v. Okay. So then we will look at a more complex examples after this, right? So now let's move on to the analytical function. Right. So now analytical function. In this topic, actually, complex variable, you're going to talk about the calculus, the differentiation, integration of a complex number. So here, that is why you come across this term analytical function. So analytical function, it comes about when you take the differentiation of the function with respect to the complex number z, right? So now when you differentiate the function f prime over here, so this you are going to write as df over dz, the usual notation. There's nothing new. And again, the definition is also the usual way that you define the differentiation. So you have this equals to delta f over delta z, and when this is equals to this, when your delta z is approaching 0. So when your increment is very, very small. Okay. And this here is going to be equals to this part, right? This part is going to be fx plus delta x minus fz. Okay, so you have right. So let's just draw this a line, and now let's say this is z, and this is z prime. So this is delta z, right? So the f delta f divided by delta z is just the change in the y-axis divided by the x-axis. Right, so this is normal, right? So that is the differentiation part. And now, if you look at this regular function, which is a function f depending on one variable, so this is x only. So f dependent on x, and now we are going to plot this. So I assume that this is a straight line. Okay, so if you look at the straight line, here we can say that this function is an analytical function. Okay, this function fx. So let's say we write now fx equals to mx plus c in the usual way. So we can say the fx is an analytical function. Why? Because we say the function is analytical if, right? Here you have f. Let me just call this as f left, fl. So you go to the right from the left, and you go here on the right. Okay. So you have the same function, but one coming from the left and one coming from the right. So at this point in space in the line, x equals to x naught, you must have the same differentiation. The same, when you differentiate the value, you should get the same value. Okay. So how do we prove that? So let's go and take from the left hand side. So let's write fl. So fl prime is going to be equals to, if you follow this notation, right? So you will have f x plus delta x minus f x divided by delta x, because there is only one variable. Okay, so there is only one variable. So in this case, so I'm going to put x plus delta x into the function because this is my function. So I'm going to replace, instead of x only, I'm going to replace x plus delta x inside. So now I have m x plus delta x plus c, right, minus fx only. So this is mx plus c, and this whole thing is going to be divided by delta x. Okay, so now you just have to expand, and you see mx minus mx is going to vanish, and you only have m delta x. So now you have m delta x over delta x, and this is equals to m. Okay, so here you will see that FL, if you approach from the left hand side, this is going to be equals to m, and you can do the same for this function coming from the right. You will see that this is also equals to m, and here you see there is no dependence on delta x, right? So it doesn't matter how you approach point.
Doktor, tak nampak.
Tak nampak? Oh, okay. Sorry. Let me see where's my view. Where is my view? Okay. Let me go down. Boleh?
Boleh, doktor.
Alright, very good. So let me continue a little bit. So here, if you look at here, from here, if you expand mx minus mx, vanish. M delta x, there is nothing to cancel here, so you have m delta x at the numerator. You have mc, but here you have here you have c, and then here you have c. This is going to cancel, and therefore at the end you have m delta x divided by delta x. Delta x is going to cancel, so this is equals to m. Okay, so it means when I want to reach this point, saya nak sampai to this point. It doesn't matter how I reach, because delta x is to show how I approach this point. Okay, so how I approach this point is not going to affect anything. Only kayo, let me just admit. Right. So this is an example for a regular function. Okay, any boleh faham eh? Okay. So let me rephrase. In a regular function, kita kata function tersebut adalah analytical or regular. Analytical sometimes can also be translated, or people use the term regular. So a regular function, an analytical function, it means kalau saya nak sampai satu point tersebut, saya tak kisah saya datang dari mana, kiri, kanan, tengah, belakang semua. Is the derivative is going to be the same, right? Okay, so that is for a regular function. So now when you go to a complex function, this is going to be complex. You know why? Because this is now when you write in terms of complex function, this is going to be a function of x. Okay, but here this is going to be y, and you have kind of like a 3D plot. Or you have x, y, and then you have z, which is your complex number. Okay, so let me just rub which one should I rub this? Maybe I rub this one. Okay, let me just throw away this part. Let me throw away this part, and let's see. So let's take, for example, now f z squared again. Okay, f z squared. Tadi kita dah buat, kita kata ini sama dengan this is equals to x squared minus y squared plus 2xyi. Right. Okay. So now in order to show this whether this function is analytical or not, there is no need for me to expand to this. Okay. So I can just use this definition over here. So here you have a function that depends on z squared, right? So when you take the differentiation, that is this, you have z plus delta z. Right, so now you have, let me see. So you have f prime, that is the definition, that is the z equals to 0. Okay, and then this is going to be z squared. Let me check. Yeah, maybe I should do that. Yep, maybe I should do that first. So this is z plus delta z minus f z divided by delta z. Right. So this is the definition. Let's just write this. So now this is limit delta z 0. So f z plus delta z. So it means this one I need to increase by delta z. So here I will have f. Okay, kita naik delta z, so this is going to be z plus delta z kuasa 2. Okay, so because my function I need to increase by delta z. Now they give me a function which depends on z squared. Okay, so it means this whole thing is my z plus delta z here. Okay, this one. And then here I have minus f z squared divided by delta z plus delta z. Right. Delta z. No, sorry, delta z. V3. Sorry. Delta z. Delta z. No, sorry. Right. So here this is limit delta z to 0. So here we are going to have to expand this one. So this is going to be z squared. Okay, and then I have plus f 2z delta z minus f z squared divided by delta z. Okay, so now f z squared and minus f z squared is going to cancel. Did I use a more difficult notation here? Yeah. Sorry. I missed something. Yeah, sorry. Let me just rub this one. It's not so complicated. Sorry. Here. So wait, because I have already put. I'm going to put this one inside, right? So z plus delta z. So here I would have z plus delta z squared, and this is going to be fz. This is going to be z squared, right? And then you have delta z. Yeah. So this is the one that I want. So faham tak kenapa jadi macam ni? Sebab yang ni this is the definition, right? So let us this is the definition. So now saya nak function yang saya naikkan sebanyak delta z. So function yang dia bagi ialah f z squared. Okay, dia bagi f z squared. So maknanya saya punya z ni kena naik sebanyak delta z. So I have z plus delta z, then I have to take it squared. Okay, so now this is this minus z squared is coming from here. Sebab my function yang asal ialah z squared. So now here I have z squared. Let me just write this down. Minus 2z delta z minus z squared over delta z. So here z squared and z squared will cancel, right? So you have so here you have right. Here you have minus 2. Sorry, plus. This is going to go plus. So plus 2z delta z divided by delta z. So delta z and delta z is going to vanish. So this is going to be 2z. Right. So so here we see that this function is analytical, right? So because no, doesn't matter how delta z approaches 0. So delta z approaches 0 means you akan sampai kepada point yang you nak. Okay. So kalau in this case there is no delta z because delta z and delta z is going to cancel. So it means now this function is analytical because delta z is how you approach that point. So there is no dependence on that. So it means this function z squared is analytical. Okay. Okay. Example number 2. Example number 1 just now. Example number 2. And this we show that this is also an analytical function. Boleh semua? Boleh, yeah. So if you look into the book, right? So now this, if I plot this on a complex plane, and then let's call this point as z0, right? So let's call this point as z0. Okay. So here, when you say you want to reach this point, so here you can have many ways, because now your z is a function of x plus iy, right? So now if you have z squared, you have z x squared minus y squared, then you have to xy on the y-axis. So here this is my explain my real part, and this one is on my imaginary part. So if you want to reach this point, there is many ways. So you can go through here, you can go through here, or like in the book, they give a very nice representation. You can spiral it, and then you can reach to this point. It is also possible, is it? So so delta z over here is to show that how you want to reach this point. So you can reach this point by going through this path, that is, you go from upwards. So in upwards, if you follow this path, right? So this is going to be delta z. So delta z is going to be equals to delta x plus I delta y. Okay, but in this case, my delta x is going to be 0. So this is going to be I delta y only. So I'm going to increase, I'm going to increase, and then I reach the point that I want. So if you want to go from this way, this way, this is going to be delta y equals to 0, because there is no change in y. And then you have delta x. So you have delta x will slowly increase, and then finally they reach this one. So the whole point is, when this analytical function, it means that the function is analytical if the derivative around this point is the same. Okay. How you want to imagine this in a regular function? So I kind of like let's say you have this point here, right? x0. So take for example the case of a barrier in the quantum mechanics. Then in quantum mechanics they say I'm not sure whether you have learned this. So you have a boundary condition, and then if let's say this is region 1 and this is region 2, and then you have if you have a function like this. So at this point, let's write in terms of the usual notation, my x0. So this is from the left hand side. So this is my psi left, and this is my psi right. Okay, so my psi coming from the left hand side must be equals to psi coming from the right hand side. Okay, and then in this function, the derivative also must be the same. X0. So pada titik ini, dia punya function dia punya point sama. This means they are exactly at the same point, right? Okay, and then the next one derivative, it says the slope must be the same. Okay, so kalau slope tak sama, then you're going to have a line, a crooked line, something like this, right? You have a barrier here, and then you have a function. Is it too small for you? No. So you have a function. Let's say for example, satu macam ini, satu macam ini. Okay. So this is not a continuous function because you have a break. Right. So that is the meaning of this is a way of how to understand the analytical function. Okay. Right. So one more example, which is given in the book, which is very nice. Here, let me just drop this one. Right. So this again, analytical function. So let's look at a function which is dependent on absolute of delta of z. You find a function that is absolute of z in this case, right? So here, if you want to take the f prime, f prime, this is going to be So this is going to be let me just write this one. Right, tends to 0. Right, so here you have z plus delta z, okay, minus z divided by delta z. So the delta z dekat bawah ni we don't disturb. We change the function over here. So the function now in this case the function is z squared. So now we are going to change the function to absolute of z. So when you put it inside, you have absolute of z plus delta z, and then here you have z, right? So squared. So this is squared. This is going to be squared. This is squared, right? So now let me just right. So now when you expand this, you will get this as z squared plus 2z delta z minus z squared, and this is delta z. So now here you have a limit blah. So here z absolute of z squared, and this one is going to cancel, right? So now you have 2z delta z, right? Yeah. Or you can, or let's just simply write this as limit 2 z delta z delta z. Okay. So here, I was a little bit rushing. As z equal to 0. And I reached the point I want, I guess. Did I miss something? I missed something. Okay, fine. Let's drop this. I missed something over here because I forgot my delta z. Let's see. So here I have a plus delta z squared minus z squared. Okay, so again, this and this is going to cancel. So now you have two terms over here. 2 z delta z plus delta z squared divided by delta z. Okay, right? So this is the point that I want to reach. So now, if you look at this, it looks similar to the one over there. Oh, same as usual. I forgot delta z over here. I forgot delta z. Okay. So guys and girls. So here I missed out delta z over here. So there is a plus delta z squared. So I'm going to cancel. So I have a plus delta. Right. Did I? Okay. So let's come back to this. So in this case, here you will see that the what we call that. Now you have a kind of a similar equation to the left hand side, but on this in this case, here this is a real number. Okay, so this is a real number. This is a real number. So now when your delta z tends to 0, then what is the outcome? So here delta z, this is going to be a complex number. So this is going to be a real number, right? So at the end of the day, this is going to be a complex number as well, because now this is a non-analytical function, right? So how do we see? So again, we go to the line just now, and this is my x and this is my y. So now delta z is an imaginary number. Sorry, this is a complex number. So when this is a complex number, so let's say you have a point over here, you want to reach this point. This is not this. There are many ways to go through it. So let's say, for example, delta x, you increase in a straight line. So delta x is going to be delta z. Sorry, delta z is going to be delta x plus I delta y, right? So you're going to increase in a small direction, and then you will reach this point, right? So this is so there is no way to simplify this, and therefore this is a non-analytical function, right? So why this is non-analytical is because this is a real part, this is the imaginary part. And remember, when we want to kind of like simplify this, so we multiply this by the conjugate, and then we also multiply the top by the conjugate, and therefore at the end you have an imaginary part as well. So when you have imaginary part as well, so you have a delta. You're going to be able to what we call to reach the same point, but the derivative is not going to be the same. Okay. Let me just go back to the one on the left. Let me check. Let me see, where am I? Let me minus. Here. Yeah, I think I didn't do a very good job here. Let me just write this. Let me just also write this. Let me just put this back again. It's like delta plus delta z squared minus z squared, right? So, right. So I come back to the left hand side first. The left hand side again, the function which is z squared. Z squared. Now you will see that again I forgot delta z. So if I know, I put in delta z again. Delta z. So to differentiate with two, sometimes you get confused with it. So here, is this? Yes, this is it. So now I got limit delta z equal tends to 0. So again, cancel off. So I have 2z delta z plus delta z squared, right? Divided by delta z. And now I have a limit delta z tends to 0. So here when I differentiate them, then when I cancel them off, then I will have 2z plus delta z. Everyone with me? Yes? Is everyone with me? Yes, very good, Faris, thank you. So here you see, when after I simplify, earlier I forgot one. I have 2z plus delta z. Okay, I have a plus delta z here. So now when I say limit delta z tends to 0, right? So when I have, yeah, you can see. So when delta z tends to 0, so this one is going to be vanishing. So I will only have 2z at the end. Okay. So it means it doesn't matter how my delta z is going to decrease. So I can decrease delta z by going this way, going this way, going this way, right? So my derivative is still going to be the same. Okay, but so this shows that this is an analytical function, right? Whereas on the right hand side here, again, we didn't do the mathematics well. We didn't simplify everything, right? So but here you just have to notice that this is a real number, Okay, this is a complex number. This one divided by this one, you are going to get a complex number. Okay, which you will see delta z appearing in it. I hope it's okay. So you'll see delta z is appearing in it. So it means now your f prime is going to depend on delta z. So where you approach that point is going to change your f prime. So therefore, this is a non-analytical function. So check part one to understand what is analytical function. So these are the checkpoint in today's lecture. Okay, any question? If no question, I think the best way to approach this topic is to do some exercises, and that is why I want to do it over a live session. Right. So here I see Faris has some question. A question. Dr. Shift ke kanan sikit. So I shift ke kanan sikit. You mean my this one? Let me see. Oh, no. No, the other side. Yes. Boleh? Boleh, Faris? Okay. Faris asks, bukan patutnya equation sama. It's a very interesting point, you see, because z squared, tapi yang beza cuma ada modulus saja. Okay, so now the modulus is the one that is doing the trick, you see, because now this is absolute value, right? So but then you are in a complex place, so you have x and y, right? So now you want to reach this point, you have to see how to go in this complex plane. But then now when you do the derivation, right? So dekat sini, where am I? So again, this is your definition, right? So here you are putting in z plus delta z, the complex number, okay, as it is. Whereas in this case, you are putting the absolute value, okay? So absolute value over here, absolute value over here. But this delta z, that is the one at the bottom of the denominator over here, this is a complex number. Okay, so the form at the top here, if you look at this one, it is the same. It is the same, except for my modulus. So bila saya ambil modulus ni, so now this is a real number, this is a complex number. So automatically yang ambil ni bahagi ni akan dapat a complex number. Macam kita ambil sorry. So where am I going to write? For example, you have 1 plus I bahagi dengan 1 plus I, sorry. 1 plus I. This is something like a 1 divided by 1 plus I. So when you multiply this by 1 minus I, you multiply this by 1 minus I. Okay, so at the top here you have 1 minus I. At the bottom you have 2, right? 1 plus 1. 1 times 1 plus 1, this is 2. So the real part you have 1 here, and here you have this imaginary part. So now this one, your denominator is not 2, but it's delta z. So you have a function which is, let's say this is a real number, right? So let's put this as normal x only. So now delta z you have to multiply by the complex, the conjugate, and then here you have multiplied by the conjugate as well. So here jadi real number, tapi sini jadi imaginary number again. And you have a delta z here, right? So it means now so this function is not analytical because you have a function of delta z. So delta z dia berubah, delta z berubah, your f prime akan berubah. So maksudnya kalau saya ada this, let me just go to the top a little bit. So if I approach this as a straight line, okay, my delta z is going to be delta x plus I delta y. Okay, so I have one value of f prime. Tapi sekarang kalau saya nak buat macam ini, maybe want to reach like this, okay, I want to reach like this. So now my delta z is going to be different, and I have a different value of f prime. Okay, so that is why this is not analytical anymore. This is non-analytical anymore. And yeah. Another question, let me see. Data Z yang belah kiri tu tak boleh bawa keluar. This one is sebelah kiri. Sebelah kiri is what? Faris yang mana? Yang ini? Yes, yang ini data ni modulus. You cannot bawa keluar ni. Remember, this is a complex number. This is the modulus of. And so what is modulus? Remember, sampai sini. Yep. Yep. So delta z plus delta z plus equals for a straight line. Okay, for a straight line, delta z equals to delta x plus I delta y. So now this whole expression is this one. Okay, assuming a straight line, you can use whatever line you want. But assuming a straight line, so this is my delta z. My modulus now. Delta z is going to be delta x squared plus delta y squared. So dia tak sama. So you cannot say delta z is the same, then I just want to cancel tak boleh. Okay, very good question. I think this is a very important thing to remember. Okay, dalam in any equations, you have to be very careful when you talk about absolute, because now absolute and absolute z and z is not the same anymore. Okay, remember kalau kita ada complex number, you take the absolute, it will give you kind of like the radius in a circle. And whereas the z itself is different thing. Good. Very good. So ada soalan lain. This topic is very abstract, I would say lah. So kalau ada apa-apa soalan yang you rasa mungkin macam sedang sangat pun tanya, right? Because then we can discuss together. Right. So let me. Okay. So tak apa, kita teruskan because the day is long. Oh, the day is long. Let me just present this question. Where am I? Right. So I'm sharing with you now the first exercise that we want to do. So I have also posted this exercise in e-learning. I have there are two exercises. So we are going to do some of them, right? So I will need some time to wipe off my whiteboard. So now please do exercise number 1. We want to find the real and imaginary parts of this function. Okay. So you want to find the imaginary parts of the following function. We do number 1 first. Z to the power of 3. It will give me what is the real part and what is the imaginary part of the function. That is what is u, what is v. Okay. So I switch off my camera. I switch off my camera for a while, and then you will tell me your answer after this. Okay, boleh semua tolong buat sekarang. Tolong buat soalan nombor 1. Z to the power of 3. So how is the progress? If you have completed number 1, that is z to the power of 3, please go and do number 6 now. E to the power of z. E to the power of z. Find the real part and the imaginary parts. Semua dah siap? Nombor 1, number 1. Dah. Okay, because I asked in the chat but no answer, so I don't know. Right, so let me just show you my whiteboard now. Very good. Let me see where. Yeah. Okay. So let's go and look at the left-hand side. Left-hand side, I asked to find the real parts of z to the power of 3. So this is the usual thing. You just expand them, blah 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 blah, and then you got this answer. We have x to the power of 3 minus 3xy squared. So this is my u. The real part of this function is this u equals to x power 3 minus 3xy squared. Betul? Sama? And then the imaginary part, which is for this function, the function now, this is v equals to 3x squared y minus y to the power of 3. Boleh? Dah, very good. So saya rasa semua boleh buat yang ini. This is my the function u and the function v of this function z to the power of 3. Okay, and on the right hand side here, I want to show you the same approach that we did just now in order to prove show whether this function z to the power of 3 is analytical or not. Right? So what I do again, I write my definition. I have my f prime is not equals to this limit delta z tending to 0, and now my function is z plus delta z. I need to take the power of 3, and then this is the initial, which is f to z to the power of 3 divided by the change in the complex number delta z. So now when I put this is now I have to expand z plus delta z to the power of 3. So here this is done on this part of the whiteboard. Let me see this part. Okay, so what I did is I just expand them, no problem. I think you can do it. And then the final one is z to the power of 3 plus 3z squared times delta z plus 3z delta z squared plus delta z to the power of 3. Okay, so this is for this part. Okay, this is for this part. So now I need to minus z to the power of 3. So this leading term vanishes, right? So there we don't have this term. And this remaining term you have to divide by delta z. So after you divide by delta z, for example, you see this one vanishes, so you have now 3z squared. This one, you cancel 1, so you have 3z delta z over here. And then delta z, now this to the power of 3 divided by 1 delta z, now you have delta z squared. Okay? So now, again, this is a definition of the definition of a derivative is to find delta z tending to 0, right? So when delta z tending to 0, you see this is going to be 0, this term is going to be 0, and this term is going to be 0 as well. Okay, so therefore, f prime is equals to 3z squared, and you see that this shows that z to the power of 3 is n, analytical function. Okay, let's just go down a little bit. Okay, so here you prove that this is an analytical function. So okay, everyone. Yes. Yes. No. Yes. Boleh. Screen kecil. Screen saya kecil ke screen Faris kecil? Ke saya tulis kecil sangat? Doctor, I can see. Farhana. Oh, Farhana said you cannot see. Which part you cannot see? Faris also. Sebelah sini boleh nampak.
Doktor punya slide kat komputer yang besar.
Ah, sorry, I forgot to stop sharing. Thank you for telling me. So I stopped sharing. Now you have a full screen, right? Sekarang full screen. Yep. Okay. Very good. Right. So let me repeat. Sorry. Remind me again if I forgot to stop sharing. So let me repeat. Z to the power of 3. I expand this. I do my simple stuff, and now I got u equals to this value. Okay. This term. V, which is the function in the imaginary part of the complex number, is 3x squared y minus y to the power of 3. Sama semua? Yes, very good. I hope. Rasanya sama apa?
Sama-sama.
Sama-sama, okay. So now, this is to answer question number 1. They ask you to find the real and imaginary part. So this is the real and the imaginary part of this function z to the power of 3. So on the right hand side, that's plus ini. I want to show whether this function is analytical or not. Okay, and I use the same approach that we did earlier. That is, I use this definition, the f z plus delta z minus f z divided by delta z, right? So, but now the only difference is this term entering the function is to the power of 3 because this is z to the power of 3. And then now when I put in the function, I have z plus delta z to the power of 3 minus z to the power of 3 here. So now I need to expand this term. So I have expanded like this, the usual stuff like you did for that. Okay, you do one by one. So this is I expand 2 first. Then after that I multiply them. You can use whatever technique that you want, but I'm just showing the easiest way, I guess. So here I have now this term, right, which is z to the power of 3 plus 3z squared delta z, 3z delta z squared plus delta z to the power of 3. Okay, so this term is the one that I get when I expand this one. Okay, so now I need to minus z to the power of 3 here. So it means my first order term here is going to vanish. So this and this is going to cancel off. So I have the remaining term here. So the remaining term now I need to divide by delta z. So when I divide by delta z, this one is going to be equals to 3z squared only. Here 3z delta z squared, this one I'm going to cancel 1, so this is 3z delta z. And this is, I'm going to cancel 1 also, so this is delta z squared. Okay? So this whole thing now is this whole part. So now I still have this limit, the limit over here, delta z tending to 0. So when delta z tending to 0, delta z tending to 0, I will have this one equals to 0, and this one equals to 0 as well. So I only have the remaining one is f prime equals to 3z squared. Okay, and because there is no dependence on delta z now, because if I have a dependence on delta z, means my path is going to play a role. So when I don't have the delta z now, 3z squared, it means this z to the power of 3 is an analytical function. Okay. Right. Boleh semua? Boleh. Very good. Boleh. Right. So I remember I asked you to do number 6. We put that on hold, and now I want to introduce to you the other term, which is the Cauchy-Reymond's condition. Cauchy-Reymond's condition. So you see, in order to prove whether z to the power of 3 is analytical or not, I have to do a little bit of kind of a slightly long derivation in order to show. But I can use a simpler approach that is using the Cauchy-Reymond's condition, and and the answer is here. Okay, so this part. But before that, let me just show you the slides to kind of like a synthesize, what is the Cauchy-Riemann condition. There are many theorems, but I just show you the first 4 theorems. That is enough for this one, right? Enough for our topics. Right, let me just go to my presentation. Okay, where am I? Okay. Window. Complex. Okay, nampak this slide? Oh, let me see. Let me just enlarge. Do you manage to see the slide now? Jangan pandang whiteboard dulu. Okay. Right. Yes. Okay. Very good. So let me just show you the. You want to screenshot, right? So let me just now let me just bring you all through a short walk on Cauchy-Riemann's theorem conditions theorem. So there are many theorems here. Let's go to the first one. Oh, so sorry. So now let's go to the first one. I need to pointer. Yep. So let me just go to this one. So theorem number 1. Here they say if you want to show the function is analytic or not, so now you write the function as in terms of u and v. Okay. Macam tadi kita dapat z to the power of 3, u kita ialah berapa? Z x kuasa 3 tolak 3x y kuasa 2 kan. So that is my u. And that the same goes for my v. Okay. So now if I want to show that this is analytic or not, I just have to take a partial derivative of u as respect to x. Maknanya yang ini saya partial derivative, ambil the partial derivative with respect to x only. And kalau dia sama dengan partial derivative of v with respect to y. Okay, so now I take this partial derivative of this with respect to y. Kalau sama, it means the function is analytic. Okay, so this is when you take the partial derivative of u with respect to x. But now kalau kita ambil partial derivative of u with respect to y, now this is going to be equals to the negative of the partial derivative of v with respect to x. Okay, dia terbalik saja. So kalau kita ingat yang ini senang. Kalau kita ingat yang ini du, partial derivative tapi kita panggil du sajalah. Du dx sama dengan dv dy. So it means is analytical. Tapi kadang-kadang kalau kita tak boleh take a partial derivative of y for some reasons, right? So kita boleh ambil kita tak boleh ambil partial derivative of u with respect to x. So kita kena ambil du dy. So kalau kita ambil du dy, kita kena ingat yang sebelah kanan tu, yang v ni kita akan ambil dv dx, tapi dia ada negatif. So kalau yang ini pun bermakna the function is analytical. Okay, so this is the theorem number 1. Now theorem number 2, it says if u x, y, and v x, y and their partial derivative with respect to x and y are continuous and satisfy the Cauchy-Riemann conditions in a region, then f is analytic at all points inside the region. Not necessarily on the boundary. Okay, so here it means kalau macam tadi kita z to the power of 3 ni dia punya, kita dah tunjuk dia analytical kan. So it means kalau kita ada region, if there is a region, if you plot this, then you will see that inside the region the function is going to be analytic. Okay, so that is the theorem number 2. So theorem number 2 yang ni dia tak proof. Theorem number 1 they actually prove it in the book, but I'm not going to show you because you can just refer it in the book. Very straightforward. What I'm more interested is to apply this. I want you all to be able to use this, and then you do it often, and then you will be able to appreciate what it is. So I won't show the derivation here. Then here I put some definition. If fz is a point at which f is analytic, then it means z this is regular point. A regular point maknanya analytical point pun boleh. Tapi biasanya kita kata regular point. This is in contrast to singular point. Mungkin kalau you read some books, then you will come across this word. They always say singularity. It means at this point the function is not analytic. Okay, so a point where the function is not analytic, we call it as a singular point. Okay, so you will see this term a lot, especially when you talk about I don't remember, black hole, I think, right? So now let's go to theorem number 3. Theorem number 3. Here again, they say there is no proof, but here it says if fz is an analytic in a region, then it has derivative of all orders at points inside the region and can be expanded in a Taylor series about any point z not inside the region. So yang ini bermaksud kalau f ni ialah analytic, maknanya kita ada derivative of all order. Maknanya kita boleh ambil df dz, df squared, dz squared. You know, there's you have a different you have different orders in n. Right, so this is theorem 3. Now the next one, theorem 4, is very important because this is this is what we also included in our course content. So here you will come across Laplace equation. So I will write down later what is Laplace equation. Very simple equation. So it means kalau f is equals to u plus iv. Okay, kita tulis macam bentuk macam ini. It is analytic in the region. Okay, so this function has not necessarily will be analytic in all space, in the whole space. So it might be analytic only in a certain region. So here it says kalau dia analytic in this region, it means my u and v, this u and v will satisfy the Laplace equation. So this is very interesting because now kalau kita kata f itu ialah analytic and I give you u, you can immediately or you can try to find for me what is v. Okay, kalau f ialah analytic, kita tahu u, kita boleh cari v. Kalau kita tahu v, kita boleh cari u. Okay, and this is based on the Laplace equation. Right, so yep, so now we will now look at the applications of the Cauchy-Riemann's theorem. So let me just stop sharing now. Maybe before I stop sharing, any questions that you want to ask about these few things that I have explained here? Stop sharing. Someone left the group. Okay. I will share later. Okay. So tadi siapa kata Alia nak ambil gambar? I will upload the slide in the e-learning later. So there are a few more theorems, you see, because they have theorem number 5, number 6 on the counter integral, and counter integral dia akan relate kepada apa yang kita belajar dalam vector analysis, the Green's theorem, where you have the integration over a closed loop, right? But I think I won't go into there. Then we have time to go into metrics after this. Okay, but it is very interesting if you see how things relate from one topic to another. Okay, so Farhana, to menjawab soalan, saya akan masukkan dalam e-learning lepas ni. So I think I need to shift my head a little bit because Alia wants to take a picture of it. Okay, Alia. Now, so can I? Okay, done. Very good. Right, very good. So nanti saya akan share dalam. I will post this lecture online as well. Okay. So now again, this is using the definition just now that we discussed earlier on, how to prove that the function is analytic or not. Now I can use the Cauchy-Riemann's condition in order to prove that this is analytic. How? If you look at this is my u now. I will take the differentiation with respect to x. Okay, I take a differentiation with respect to x, then I will have 3x squared minus 3y squared. Okay, now I take v, I take a differentiation with respect to y. So now this I will have 3x squared, and then this I will have 3y squared, right? So now you see this and this is exactly the same, and therefore this what we call that? Yeah, and therefore this is an analytical function. No, this is an analytical function. Okay, z to the power of 3 is an analytical function. Okay, now this u and v, you will see that they obey the Laplace equation. Laplace equation, and when you prove that u and v obeys the Laplace equation, you will call them, these are called harmonic functions. This guy and this guy. Okay. So again, let's see. If the u and v of this any function, they satisfy the Cauchy-Riemann's condition, which means du over dx is equals to dv over dy, or du dy equals to negative of dv dx. Then this function, whatever functions that it is over here, this is analytical, right? And u and v is a harmonic function because they satisfy the Laplace equation. So it's also the other way around. So if you satisfy the Laplace equation, then you can show that this is also an analytical function in that region. Okay, right. So this is example number 1. So let me go to now question number. I think we look at one more example. So what time is it now? Do I have time? 11:30. We will try to cover a little bit more. Here. So now I want to show you the answer for number 6, exponential z. Have you got the answer? If you those who have the answer, please write it on the chat, and you tell me what is your real part and what is your imaginary part of exponential z. No. Exponential z. Tak ada orang bagi jawapan ke belum lagi? Dah siap ke belum? What is tanda soal? Faris, I ask you to find the exponential z. What is the real part or the imaginary part of it? Z. Oh, okay. Right. Now I see. Just now it wasn't there. Nabila. Okay. So yang lain dapat sama? Yang lain dapat sama tak? Because here now you have E x plus I y, right? Okay, so now you have to expand z is equals to x plus I y. So this is equals to exponential x dot e I y. Okay, so now this is e x. This is cos y plus I sine y. Okay, so now so what is u? Let's talk about u. So u is going to be is u equals to ex or ex cos y. Yang mana satu ialah u? Siapa kata A? Siapa kata B? A atau B? Remember, we define u as the real part of the function f. Huh? Saya kata A. B, A. Saya kata A. Saya kata C. Alright. So, what about the others? A, right. Okay, so the real part, you must take this one multiplied by this one multiplied by this one. Okay, so the answer is B. Oh, ramai kata tak salah. So this is going to be ex cos y plus ex sin y I. Okay, so ni kalau macam dia macam very confusing but here if you treat this as a normal complex number, let's say you put this one as z prime now, okay, z prime, and then you will see where's my imaginary part, where's my I is over here, so this is the imaginary part. So so this is the let's write this as v now, v, and this is the real part of the complex number, so this is u. Okay, so tadi jawapan tadi ialah B. B kan? Yes. Okay, everyone agree? Nampak? Faham This is a tricky question. Tapi kena ingat. Apa-apa nombor kat sini kena darab. So let me just take for example. Now let's take for example the exponential iz. Let's say exponential iz sekarang. Exponential iz kalau kita expand exponential I x plus I y, right? So this is going to be exponential I x minus y. So this is going to be exponential minus y dot exponential I x. Okay, so sama. But this is not interesting. One more which is more interesting, right? Now how about this one? How about something like this? Let's call z prime. Z prime equals to 1 plus I. Okay, exponential z. Okay, z prime exponential z. So here kita ingat tak, kita kata boleh tukar kepada polar form, right? So this one is going to be equals to square root of 2 exponential I pi over 4. And here exponential z. Okay, so here this is going to be square root of 2. This is ei pi over 4. This is going to be ex plus iy. So this is like we did just now. This is ex eiy, right? So now we have square root of 2. We have ex And then here you have e I y plus pi over 4. Okay, so now this is going to be cos y plus pi over 4 plus I sine y plus pi over 4. Okay, so the real part now is not this one. The real part is this one multiplied by this one. Okay, so you got to be very careful when you deal with complex number like this. Okay, so now faham yang ni? Yang ni faham? Ada soalan? Faham, very good, faham. Okay, so now let's now this one. So now my u is equals to e x cos y, v is equals to e x sin y. Sekarang saya nak minta you tolong guna Cauchy-Riemann condition tadi untuk tunjukkan sama ada exponential z ini ialah analytical function atau tidak. Right? You use the Riemann's theorem, Cauchy-Riemann's condition just now to show whether exponential z is analytical function or not. Okay, so take a few minutes. Let's try to do it. So just now the Cauchy-Riemann's condition is delta partial derivative of u with respect to x is equals to v y or n u y goes to minus v x. Okay. So now what you need to do is let's take this one. So you take the x y. What do you get?
EX cos Y.
Yeah, very good. So ex cos y. So if you take now partial derivative of v, which is ex sin y, what do you get?
EX cos Y.
Ex cos y, very good. Right? So here you see these are the same. These are the same, and therefore exponential z is an analytical function. Right? So if you want to use this one, you'll see that this is going to be the same. It should be the same, right? So du dy. So let's take du dy. So this is dy. U again is ex sin y. Cos y. Cos y. So this is going to be negative ex sin y. Dv. Now let's take dv. Dx is equals to v is ex sin y. So dx, this is going to be ex sin y. Okay. So this, you see there is a negative here. So when you multiply negative, then you cancel, and this is the same. Okay. Okay. So that. So we have done, and now we have done with the second part, and we will reach the last part, which is on the Laplace equation. Okay, Laplace equation. So we we can use this example. Okay, let me just run this. Okay. So now we go to Laplace equation. Laplace equation and harmonic function. So Laplace equation is this one. You don't have to put. You have to put the vector, but you can actually you can put the vector, right? But because this is our usual gradient, I dx plus j dy. So in a 2D, because now we are dealing with a 2D, so this is a 2D, right? So when you take del dot del gradient del dot del, sorry, so you are going to have d squared dx squared plus squared dy squared. Okay, so Laplace equation is this equals to 0. Okay, so let me just write this one. So so any function, let me repeat. This is a Laplace equation where you take the Laplace square of this function. This is equals to 0. So any function that fulfills this Laplace equation, this is a harmonic function. Okay. So this is a harmonic function. So in the theorem number 4, it says that if u and if a function of a complex number is analytic in a region, then you will have the Cauchy-Riemann's condition, which is fulfilled by u and v in this case. And then in this case, u and v is they also fulfills the Laplace equation in that region. So it means if I put this thing inside here, I will get this equals to 0. So let's try to prove. Okay, so we take u equals to ex cos y. So now when you take Laplace squared u, it means now I have let me just write in full first, dx squared plus dy squared. Okay, and this is u. Okay, so here now I have to take a partial derivative of a second order for u. So if you take a partial derivative once, right, you will get back the same equation. Twice, you will get back the same equation. Right, you have e x cos y. On this case, on this side, so you have to take a first partial derivative. So if you take a first partial derivative, you're going to get ex sine y. Do you differentiate one more time? You are going to get minus ex cos y. Okay, so here you have minus ex cos y, and you see this is the same, and therefore you have this equals to 0. Boleh? Okay. So here in this case, you can also replace by v. If you replace this by v, and then you will see that they also obey the Laplace equation. Okay. So in this case, u and v they are harmonic function, but we also call them conjugate, right? Because why it's called conjugate is because now if you know your u, if I tell you what is your u, you can find what is v. Okay, so so vice versa. If you know what is v, then you can find what is u. right? So I guess this one more part, and then we are done, and then we will see if we have time for exercise or not, or maybe we arrange another session for the exercise. Okay. So let me see, what is the example that I want to give you? Yeah, maybe we can use this. Maybe we can use this example first. Let's see. Okay, so right, everyone with me, right? Still with me? 18 of you. Okay, yeah, 18 of us. Right. So we can take the example like this. Let's say we do not know V. Okay, you know what is V now, but assume that you don't know what is V, and you only know what is U. Okay, so now you have U equals to EX cos Y. And then we are going to use the Cauchy-Reymond's condition earlier, where you have U x, this is equals to dv over dy. Okay, so let me remind you. Let's say we do not know what is v. We know what is u. We want to find v. Okay, so now you know the u. So you will take the partial derivative of this guy. So when you take the partial derivative of this guy, du x, then you are going to get ex cos y, right? So ex cos y, and this is going to be equals to partial derivative of v with respect to y. Boleh? Betul semua ini? Yes? Yes? No?
Betul.
Betul. Okay, very good. So I just want to check that you are with me, and because after this you will see it's a little bit complicated. Right. So now, first thing, kalau saya bagi yang ini, you take the derivative of this with respect to x, sebab kita nak guna condition the Cauchy-Riemann condition. Right, and then you will know that this is equals to partial derivative of v with respect to y. So now we will go to this one. So this time I want to find what is v. So I want to find what is v. What do? I take the integration with respect to y, right? So if I take the differentiation with respect, the integration with respect to y, I will now get v equals to integrate this with respect to y, ex cos y dy, and this is equals to here. So this is minus ex sine y divided by 1, fine. And then I have g here, a constant. So this g, this is a constant. Okay. So now I want to find what is g. Let me see how much space. Okay. So now when I have this, I want to find what is g. I use the second condition, that is the partial derivative of v with respect to y. Sorry, x. Yes. Okay, I take a partial derivative of this v with respect to x, and what do I get? I have exponential x here, sine y, I didn't disturb it, and now g, I do not know what is g, so I put g prime, but I just put the note here x to say that this is a derivative with respect to x. Right. Step 2. Okay, step 3, I go back to this one. I use the second Cauchy-Riemann conditions. That is du dy, and this is going to be x. Actually, there's a minus sign. Let's just put the minus sign here because this is sine y. Okay, so now I need more space. Boleh semua sampai sekarang? Sampai step sini?
Boleh.
Boleh, bagus. Okay, so now dv dx, you get this expression, and this is going to be equals to the negative of this guy, right? So it's going to be the negative of this guy. So now dv dx, okay, going to be equals to negative of du dy. So what is my dv dx? dv dx is going to be negative ex sine y plus g x prime, and this is going to be equals to negative, so this is ex sine y. Okay, so now I have gx prime equals to, I can bring this over, so I have 2ex sine y. So now here, gx, I want to find gx now, this is equals to this. So I will take gx prime, take a partial, I take an integration with respect to x. So this is going to give me gx. This is going to be equals to 2x sine y. Okay, so now I know what is my gx. Okay, actually g now, because now I cancel this. Because my this x doesn't carry a meaning, it's just to remind me of it is being a integration with respect to x. So now I have g equals to this guy. So now I this g, again, we are here. So we have to plug back into it. So that now my v is equals to minus ex sine y plus my g. So this is 2ex sine y, and this is going to be equals to, saying you have ex sine y. Right, so that is how you use the Laplace equation, because it fulfills the Laplace equation, right? So then you use the Cauchy-Riemann condition. The first one, you find v, which is, now you have a term which you do not know what is the g. This is a g which you do not know what it is. And then you use the second condition. You take the partial derivative with respect to the other variable, in this case x. So you have now gx prime, okay, a function g which you now differentiate with respect to x. Now you want to find this guy. So now you use the second condition again. Then you equate this with negative of du over dy. Du dy you can find because you are given this function. So now you just plug in this value, this term and this term into it, and you find what is gx prime, okay? And then you want to find gx, you take the integration with respect to x, got the g, you got the answer, and then you put the g back into this guy, into this expression, then finally you got v. So now you got u, you got v, okay? But this works because u and v fulfills the Laplace equation. So Laplace equation, what is Laplace equation? You have this equals to 0. Okay. So lepas ni dalam apa-apa kelas, make sure lecturer tanya apa tu Laplace equation. You remember or not? Yes, I remember. Very simple. Laplace squared phi equals to 0. Phi is any function. You nak tulis f boleh, nak tulis any kind of function boleh. But you must know this is also called a harmonic function. Okay? Boleh? Boleh kot. I think this is very fun. I hope it's fun to you. And kita tengok macam mana kita there are many concepts. You have analytical function, and then you have the you start with the real and imaginary part of the function. Then you have analytical function, and then you have the Cauchy-Riemann's condition to show that this is a harmonic function. Analytical function. And then in this analytical function, it obeys the Laplace equation, and this is how you prove this function is not obeys the Laplace equation. And in this complex function, you have a u and a v. The u is the real part, v is the imaginary part. And since it obeys the Laplace equation, u and v are called conjugate harmonic function. And if you know one, you will know the other. Okay, so basically these are the important things that I want to deliver to you guys. And I think the last one, let's look at the last example for today. It's going to be 12 o'clock. Right. Last example, okay? Last example. Last example, let's say now I given u equals to x squared minus y squared. Find v, where find v. I just put find v. Where you know v is the v is the real part of is the real number of the imaginary part of the complex function. Susah sangat. Okay, so v is a real number. Okay, a real value of the imaginary part of the complex number or complex function. Right. So now you have this. So can you all please find for me what is v? As an exercise for this one before we close the session, I give you this. The first thing that you need to do is to make sure that this obeys the Laplace equation. Okay, kalau yang ini u ni dia tak memenuhi Laplace equation, tak payah cari v. You don't have v. Okay, so now if you have u, now you show that this obeys the Laplace equation, and now you find for me what is v. Okay, last exercise for today. I switch off the video for a while, and I want you to do it on your own, and then we will compare our answer. Okay? Dah siap? Siapa dah siap? Sikit lagi. Okay, baik. Bagus. Continue first. V equals to 2xy. Right. So yang lain dapat 2xy plus something. Okay, let me just, very good Faris. Yang lain dapat tak Faris? Yang lain? So I'm not sure whether the others managed to do it. Let me just show you my screen. Here, so let me just bring this down a little bit. Here. Okay, so now let's go to this exercise. U is equals to x squared minus y squared, and we want to find v. So the first thing I show that u obeys the Laplace equation. So you just put in u into the equation here. So you'll take a second order partial derivative. You will get 2 and 2 minus 2. Then this is 0. So here you show that u is a harmonic function that obeys the Laplace equation. And then now this is the starting point where I try to find v. So here I take the partial derivative with respect to x, and this is going to be 2x. And using the Cauchy-Reymond's condition, x is equals to partial derivative of v with respect to y. And now I kind of rearrange this. I can rearrange this to here and this to here, and I integrate over y. And here I have v equals to 2xy plus g. And here I want to point out, just now I mentioned g is a constant, right? Remember in the previous example, I said g is a constant. So I make a mistake. So g is not a constant, right? So g is a function which you do not know. So g can be a constant. It can be a function, right? So let's just say g is a function. Okay. So now you want to find what is g. So now you take this, you take the partial derivative with respect to x now, the other Cauchy-Reymond's condition. You take the partial derivative with respect to x, so you have 2y. And this g is not vanishing. G is, now you have a partial derivative with respect to x, so I just denote x over here. And now, you remember the Cauchy-Reymond's condition is this one is going to be equals to the negative of this guy. So now you have to take the partial derivative of u with respect to y. So this is going to give you negative 2y, right? So now you are going to equate them together, but remember you have to take a minus sign. So cut sebelah kiri. Like this, like this. Okay. Lagi ke kiri. Ke kiri macam ni ke kiri macam ni? First one, like this. Okay, boleh? Okay. Boleh, Faris? Okay, right. So now, you remember you have to equate them, but then don't forget about the negative sign. So now when you put in the negative, so this is going to be 2y only. So you have 2y plus gx prime equals to 2y. So this one and this one are going to cancel. So gx prime is equals to 0. So it means now when you take a function, you take the when the derivative is equals to 0, it means g is a constant. So since g is a constant, now my v is equals to 2xy plus a constant. Okay, so this is the answer. So now in this case, my function f as a function of z is now x squared minus y squared. So this is my u, my real part, and the imaginary part is 2xy. So and then you have a plus a constant. So constant doesn't matter. So constant is 1. So now this is the answer. You want to find v, and then f. This is my okay. Okay. So I hope the others you managed to do it. Right. Other soalan. So now I think I will stop here and then I open for question. I see Faris got question here. Let me see. Kalau integrate 0 bukan dapat 0. No. Let me just take for example. Let's take an example. So let's say g is equals to 2x. So in this case, my dg over. Can you see? Here, no, you cannot see. And let me just shade this. Let me just like this. So if let's say you take g equals to 2x, okay, you know when you take the first derivative, that is dg over dx, you are going to get 2, okay. But now, if you write g equals to 2, that is g is equal to 2, so this is going to be dg dx is going to be equals to 0. Okay, so g can be 0, g can be equal to 0, or g can be equal to 2, 4, 6, 7, 8, 9, 10. There is no dependence on x, so this is still partial derivative equals to 0. Boleh, Faris? Boleh. Very good. So, yang lain, any question? I know it's a bit long today. It's a long day. There are many things that we have discussed. Not yet. At least belum dapat lagi. The derivation. Not yet ke tak ada soalan ke tak siap? Sorry, I misunderstood. Faham. Very good. Faham, right? So now I will ask you all to do the exercises, which I've actually posted these 2 exercises on the e-learning. So the second set of question is this one. So the second set of question is here. They ask you to find the following function satisfy. You want to show that it satisfies the Laplace equation, and then you want to find the conjugate harmonic function. Okay. So here, for example, you know what is y. Then you want to find the other function that that is the conjugate of this one. Okay. So so let me see. So here we will stop here, and then I will request you all to do the exercises. Let me see. So the plan is like this. You will try to do these exercises on your own. If you have any questions, I put there if, because if you have any questions, then we will arrange a class, hopefully maybe next week after the Raya. And if not, then I will assume that you managed to do it, and you do not have any problem. But you have to be very careful because this one, when we put it like this, it looks very easy, but then when you're actually doing it, it's going to be complicated, because you're jumping from one thing to another, and then you are trying to relate things, and things can be kind of complicated, right? So do this on your own, and then if you have any questions, please, I don't know, maybe the best way is to post it in the WhatsApp group, and then we will list the questions that you want to discuss, and then we'll make a class to discuss on it. If not, then we won't have class, and this will be the last class on complex variable. That is one thing. The second thing is I'm going to post an assignment which you need to do, and you need to submit. Okay, on the complex number and complex variables. Okay, so let me just stop here, and I open for any questions. Last 2 minutes or 3 minutes. TFI, apa is TFI? Tadi. Okay, saya ada announcement. Announcement. What I mentioned just now is I have 2 sets of exercises just now, right? Which is I posted it in the e-learning. The one is to find the real parts and imaginary parts, and you prove that this is analytical function or not. Second set of question is to prove that the function obeys the Laplace equation, and you want to find the conjugate function, right? So dua set ni, you try to do on your own. Kalau ada soalan, kalau kata okay, nombor 10 tak tahu buat, nombor 12 tak tahu buat, then you list it in the WhatsApp group or something like that, and then we arrange a class and we discuss. Okay, tapi kalau tak ada soalan, then I assume semua okay, and then this will be the last class on complex number, and we take a rest next week. I'm not sure whether we should take a rest, but we'll see. And then we will straight away go into metrics. Okay, and the second announcement just now was that I will post the assignment on complex number and complex variable that you need to do, and you need to submit. Very good. So any other questions? No.